Welcome back, everyone. This is the second session of this morning. Welcome back, everyone on the internet, on Zoom. Our next speaker, this is an invited speaker, is Tom Delworth from GFDL, and he'll be talking about the new prediction systems from GFDL. Tom, all yours.
Thanks so much for the invitation. I'm very happy to be virtually part of this meeting. And what I wanted to do, rather than present a specific research finding, was to present a bit of an overview of some of the activities we have going on at GFDL that are well aligned with this topic of seasonal and going beyond into multi-annual prediction. And we're coalesced around using a particular modeling system there at GFDL for these results. So I thought I would first start with some discussion of that modeling system, and then also, as part of that, describe the initialization systems we use, because I think actually initialization is really an important piece of moving towards longer time scale predictions. And so our goal at GFDL and what we have tried to do is to build a system that is really not quite, but almost seamless across time scales. So use essentially the same system for predictions from sub-seasonal to decadal to centennial scale climate change. And we think there are a lot of benefits of doing this. There are interactions across scales. There are similar phenomena across scales. So I think by doing that, we can shed some light on things. So we're very excited about that sort of approach. So let me first describe the SPEAR system that we use. And SPEAR is an acronym. It stands for the Seamless System for Prediction in Our System Research. You can see the highlighted letters there. And we're emphasizing prediction as a key component of this, as well as projections, but we want to have a unified framework on that. So on the left, you see the components of the SPEAR system, an atmosphere, ocean, and land model, obviously, all unified around, say, the FE3 dynamical core and the MOM6 ocean as key components of our coupled system. And we have various versions of SPEAR that we use with different resolutions. Something we call SPEAR Low is our coarsest resolution version of this. 100 kilometers in the atmosphere and the ocean. A SPEAR medium, which most of the results I'll show today will be from, using a 50-kilometer atmosphere and a 100-kilometer ocean. SPEAR high, going down to a 25-kilometer atmosphere then and a 100-kilometer ocean. And something we call SPEAR high 25, which we have a 25 kilometers in both the atmosphere and ocean. Of course, it's a more expensive model, but going to those scales, I think the air-sea interactions become more realistic, and it's quite exciting, actually. We have lots of variety of uses of our SPEAR prediction system. Sub-seasonal prediction, I won't talk about that today, but Baoxing Zhang has been leading that effort, and the model has very good skill at sub-seasonal prediction. Seasonal prediction, a documentation paper by Feiyu Liu, shows some results of that. We use the very closely related system for then decadal prediction, showed some results of that today. Xiaosong Yang leads that effort, and we have large ensembles as well. But this particular SPEAR system is one of a family of very closely related models at GFDL, all share the same code base, architecture, dynamics, etc., but are tailored a little bit for different specific purposes. SHIELD is a version with a high-res weather prediction. CM4, one of our two CMAP6 models with a higher resolution ocean, and ESM4 has the carbon cycle in our climate system. So just a word about the initialization systems. On the sub-seasonal scale, we've evaluated the skill of this system on those time scales. We use an extremely simple initialization system. In the atmosphere, we simply restore to reanalyses, MERA2 in this case. And in the ocean, simply restore SST to an observed SST data set. And just with that simple initialization, we have quite good skill, really, in looking at things like MGO prediction. I'm sure we could do better, probably, with a more comprehensive initialization system. Then on the seasonal time scale, we bring a little bit more complexity. On the atmosphere, for initialization, we simply restore to the CFSR reanalysis with SST also restored to daily. And in this system, then, we're able to actually capture a lot of things. On the ocean side, we do a more complete assimilation with XBT, Argo, CDT, moorings, etc. Our ocean reanalysis just starts in 1991 to the present. We've really designed this initialization system to be geared towards the future and towards the Argo system. That's just such a revolution in terms of observing the ocean. So we really want to take full advantage of that, and so we don't go back further. I mean, Argo starts around 2004, so we do go a little bit before that period, but really geared towards the Argo system. We also use in our seasonal prediction model something we call OTA, which stands for Ocean Tendency Adjustments. When we do the assimilation of observations into the model, there are increments that one gets, which are a measure of the inconsistency between the model and observations. We catalog those and create a cometology of those and feed those back into the free running model to try and compensate for some of the biases that a model has, because we're interested in the relationship between model bias and predictability and prediction skill. So that's one of the ways we try and reduce our drift. On the decadal scale, we have a little bit different approach. I mentioned that on the seasonal time scale, we're really geared around Argo as our ocean information. But since that really doesn't go back very far in time, you can't have a analysis of decadal hindcast that started in 1991. So we adopted a different system. In our decadal initialization, we have the atmosphere also restored to reanalysis, in this case, JRA 55. And on the ocean, all we do is restore to observed SST. So we have no subsurface ocean data incorporated into our decadal reanalysis for predictions. Our philosophy in this decadal initialization system is to tightly constrain the atmosphere and the sea surface temperature so that in the free running analysis, the fluxes, air-sea fluxes that are computed are really derived from observations. So we try and have observations in this coupled analysis system that at least have some of the characteristics of observations. And since that's what forces the ocean then goes along and behaves a little bit like the real system. So we can actually go much further back in time than with this sort of reanalysis system. We couldn't do that with the ocean initialization system that's keyed around Argo. So with that background, we'll talk about some of the efforts that we do in predictions across timescales. These are obviously, we do seasonal predictions using the SPEAR system, and relative to our previous generation model, which was called FLOR, we have much reduced errors in SST, and we have substantially improved predictions for things like ENSO and sea ice. And we also use this as our model to participate in the real-time North American multi-model ensemble. But I want to highlight at least some new findings that are relevant for this meeting. One is some work by Li Wei-Jia, just coming out this year, on potential seasonal predictability of conditions for extreme events. Noel Keenlyside asked a question in the chat yesterday, or a comment highlighting the importance of extremes, and I totally agree with that. And so this is one of our efforts. And it turns out very interestingly that in her work, she finds that for prediction, say 8-9 months in advance of extreme heat events over the US, 3 factors rule: climate change, the role of the ocean, and the role of land surface feedbacks, all of which we had some discussions about today. A second result is really predictability and predictive skill for atmospheric rivers, some 8 to 10 months in advance. And Kai-Chi Zheng is a paper on that, leading that effort. And the map shown below shows areas where we have skill, starting in July initialization and a target months of January through February. And these different areas have skill, and he goes into some nice analysis of why those particular areas have skill. We have not run these predictions more than 12 months, but it would not surprise me if when you go to 13, 14, 15 months, who knows, there could be skill in atmospheric rivers, which are obviously an extreme event in the system, a very important event. So I think that's a potentially fruitful source for skill. So moving on to a little bit longer time scale, we have seasonal to multi-annual predictions of the Kuroshio extension. Yesterday we heard a great talk by Jing-Jia Luo at GFDL, who has really been leading this effort and showing that even within our systems, we have clear multi-annual skill in the prediction of the Kuroshio current. And here's where I'd like to make the case that having these 2 initialization systems really helps. So she showed analyses on both our decadal systems and our seasonal systems. And if you remember, the initialization process is different between those two. The decadal system only uses atmosphere and sea surface temperature information. It does not use subsurface ocean conditions. So we get this multi-annual predictive skill of the Kuroshio extension, even though we're not telling the model directly anything about the subsurface state of the ocean. So by having these different ways of initializing models, we glean insights into the relative role of either the atmosphere or the subsurface ocean. So we have good skill in this. We have high skill when we have winter initialization, and Youngji described why we have that yesterday. I suspect that if we were to extend our seasonal prediction system, which has initialization including the subsurface ocean, if we were to extend those predictions to more than 12 months, I suspect that we could get an even higher level of skill, potentially even higher than we're seeing in our decadal prediction. So very exciting results there with lots of implications, I think, of climate, both over the Pacific, marine ecosystems, as well as North American climate. I think this is a really important area to push forward on more than 12-month predictions. So going out to our longer time scales, now we're using in our SPEAR decadal prediction system. We have, I think, very nice results. So this is now looking at the North Atlantic subpolar gyre. So if we look at this lower left box, time is on the x-axis and the SST is on the y-axis. So the black line here is the observed SST in the North Atlantic, rapid warming in the 1990s. And these various blue lines represent initialized decadal predictions with our older CM 2.1 system. And then we see this very large drift away from the initialized observational state. And Jerry Meal pointed out yesterday as well as an issue. This was our older system. If we move up to this top box, we see the same black line for the observations. Notice that the y-axis is considerably reduced in scale because we have such reduced drift now. These blue lines are raw predictions now in this new decadal prediction system, and the bias and error is much less. So we have very small drift in this new system comparing the old and new. So we're very happy about this. This upper right panel showed a variant, a different test of our initialization prediction system, which has some interesting aspects to it as well. This bottom right panel shows the reduction in MSE. That's the MSE ratio, the error between the new system and the old system. So as you go down more negative numbers, that means less and less error. So a 95% reduction in error. You can see for this A1 system, which is our current system we use on different leads and lags, the reduction in error is reduced dramatically. And so we have that multi-annual skill from the system in lots of different things: Sahel precipitation, reconstructed AMOC, extreme events, some regional temperature, et cetera. So very, very fruitful to look at decadal prediction driven initially from the ocean, but across a wide variety of areas. And finally, I'd like to turn to the Southern Ocean. Rika Holland gave this very nice talk yesterday about looking at predictions in the Southern Ocean and the 2016-17 extreme change in the sea ice area in the Southern Ocean. And Liping Zhang, this is a slide courtesy of her work, she's been leading our efforts on looking at the Southern Ocean across a wide range of timescales. She also has a poster in this meeting, which I would encourage you to visit. But this top left panel shows Antarctic monthly sea ice extent anomalies from 1990 to the present. And this is this big drop that was discussed yesterday. And this is a spatial view of that. This is actually a difference in sea ice from our reanalysis system, which just gets atmosphere and SST data, yet we actually recapture relatively nicely. The green areas indicate reductions in sea ice extent after this big event. So it's quite interesting when you're looking at the mechanisms. This is a multi-annual event, but lots of different things combined together. The subsurface ocean plays a role. Teleconnections from the tropics play a role. It's a really exciting event, but clearly there's multi-annual predictive skill. And one way to look at this is looking at the subsurface ocean. So this is over the Weddell Sea. This is temperature. This is a top 500 meters. Time is on the x-axis, 2011 and 2021. This is salt content on the bottom, temperature on the top. And we see that over the years preceding this big jump, we had been building up heat in the subsurface ocean and cold on the surface, and suddenly we flipped. We have some event which mixes that heat from the interior upper few hundred meters to the surface and contributes to this dramatic change in sea ice area and temperature. But this was not the only driver. This contributes to the long-term persistence of a depressed state, but wind forcing, particularly tropically forced wind stress changes, contribute to this high-frequency interannual variability. So it's a really interesting thing. We actually, as part of our seasonal prediction system, look at and decadal prediction system, we find significant skill in SST and sea ice predictions in the Southern Ocean up to leads 3 to 7 years. Finally, one point is that in some respects, we have to think of climate change as well in terms of multi-annual predictions. These are results from our large ensembles that we've done. We looked at changing risk of drought, multi-year drought over Cape Town, South Africa. This occurred a few years ago. And from our large ensembles, we estimate the changing likelihood of such an event from the 1940s to the present. And this is the probability of such an event occurring. And when we move up here, this shows the probability of such an event. And this in our model simulations is gone from essentially impossible to something like a 3% likely event. But my point here is that with the climate change, this is moving so rapidly here that on a multi-annual timescale, this changing probability of occurrence has to be taken into account. And one of the reasons is that this is a very extreme climate. It's on the edge of a the tail of a PDF where we have shifting zones, shifting precipitation zones. So multi-annual changes, in some cases, I think, need to take into account the climate change signal, not all changes. So let me just have a summary and discussion here that this SPEAR system is in use at GFDL for real-time seasonal to decadal predictions. Lots of interesting things emerging from more than seasonal timescales, multi-annual timescales. Lots of examples of seasonal to multi-annual to decadal skill. This North Pacific is really interesting. Long-term changes in atmospheric river activity, Atlantic changes, Southern Ocean changes, and then the relatively forced change as well has to be taken into consideration. Ongoing work, we're exploring the impacts of model resolution and bias on predictability across timescales. As bias is really potentially important, as well as predictability at extremes, temperature, precipitation. And there's always this ongoing trade-off of resolution, ensembles, ability to represent extremes, what you want to predict. So some of the considerations for prediction going forward are key questions. What are the physical processes that give rise to predictability? We've had a lot of interesting results talks so far. Just heard talks about the land processes and essentially the reemergence of signals. But what are the dynamical physical processes that give rise to the predictability? And then what types of models then are best suited to exploit that predictability? Are they dynamical models? Are they statistical models? Open questions in some sense. And always the question will be model composition, what type you use, resolution. And finally, initialization systems are really crucial. I think they have a lot to do with how much skill we can potentially realize on these timescales. So again, thanks so much for listening, and thanks so much for the invitation to be there, at least being here, at least virtually. Thank you.
Awesome. Thank you, Tom. It's nice to see the effect of bias correction on model drift. There's a few questions trickling in the chat. We'll wait until everyone is. We have all three speakers present. Our next speaker is Noel Keenlyside from the University of Bergen in Norway. Noel, are you there?
Thank you very much. So today I'd just like to say a few words about supermodeling, which is what we referred to. This is ensemble approaches, a new method for ensemble approaches to climate prediction. Won't be talking too much about climate prediction, but more about model errors and how to reduce them. I'd just like to start by acknowledging the people here that you see here, key contributors to this talk, and in particular Gregory Duane, who is an initiator of this, the idea of supermodeling. So just one slide of motivation. So this is a slide that shows, it's rather pessimistic in some respects because it shows the model biases in rainfall across in the tropics from over 3 generations of the CMIP. And you see remarkably similar patterns. So you see very little, in some respects, very little progress in reducing model biases. And obviously this has implications for multi-year climate prediction. So the standard approach to deal with model error is basically to have a model ensemble and to average or combine this model ensemble. So the long-term strategy to improve models is to improve the representation of key processes, for example, by increasing resolution. So we might ask ourselves, is this, are we going to be able to reduce, looking at the previous slide, are we going to be able to reduce these model biases anytime soon, just by simply increasing resolution? And are there other approaches to get increased benefits in the short term? And we believe that supermodeling is one of those. So in supermodeling, essentially a supermodel is an optimal dynamical combination of models that is superior to its individual constituent models. So in practice, what we're doing concretely, what we do is we combine multiple models, as is shown here in the schematic on the right, so that they exchange information between each other, synchronize onto a common solution, and form a new dynamical system, which is visualized here. So a new model, a supermodel. There's some slides at the end of the presentation which go into a little bit more detail about how this is done. So this is the method section that Matt was suggesting we prepare. So in the next few slides, I'm going to show you some results from 2 different supermodel implementations. The first is basically a perfect model experiment in which we combine multiple atmospheric models from the SPEEDY system. They exchange information and they're coupled every model time step. and we couple up to 4 different atmospheric models, and they are perturbed in their parameters, and they're trained using machine learning to reproduce a truth. The second approach, second setup is a coupled Earth system models. So here we're using 3 different state-of-the-art Earth system models, the MPI ESM, the CESM, and the Norwegian Earth system model. And they're connected in this case only through their ocean states, and we're using ocean data assimilation to combine a pseudo observation of these 3 different states. And this is done on a monthly timescale. So the first thing I want to show you is that we are able to improve short-term predictions, and here it's weather forecasts. So here it's with the perfect model setup, so the intermediate complexity speedo model. And you see here forecasts out to 14 days. And so my pointer's not really working here. Sorry, so the perfect model is the black, and it shows you basically the error growth due to chaotic variations. The brown and the blue lines are the imperfect models here, the error growth of these for surface temperature. The green is the average of these 2, so the standard multi-model approach. And the orange and the pink line here are 2 different approaches for training the supermodel. And these are obviously much superior to the imperfect models and are approaching the perfect model solution. So short-term predictions can be improved. We're able, looking at the climate problem, here I'm showing you the results from the 3 coupled Earth system models connected by their ocean states. We assimilate here a pseudo SST observation. And the SST observation is an optimal combination to reduce error. The left-hand panel is the SST bias from the 3 systems combined run separately. So you can see common SST biases like in the tropical Atlantic or in the Gulf Stream. The right is the supermodel result, and you can see that the errors are dramatically reduced everywhere. You can see the RMS error in red is reduced globally. So there's clear reductions and improvements, but that was what we have essentially trained to reproduce. Here you see the results for rainfall. The top is the observed rainfall distribution. The middle panel is when we've optimally combined the models, and the bottom is the average of the 3 models run separately. So you can see the double ITCZ error is corrected in the middle panel. In the Pacific, you see the distribution of rainfall in the tropical Atlantic is also much improved. So these type of improvements are things that you cannot get, that you get in the supermodel, that you cannot get actually by averaging the outputs of the separately run models. So there's some kind of a non-linear correction for correcting model errors at an early stage. So we achieve a new dynamical system, and to show you that, I'm showing you an index here for the NINU 3 region, so an index of ENSO. The left panel shows you the 3 different models run separately, so they're not synchronized at all, as you would expect. The right panel is the supermodel result, and so you can see that we do achieve an ENSO variability. It's a little bit weak, but it's reasonable, I would say. And then just one slide about how we're doing for climate change to longer time scales. So we've produced a new dynamical system, and this is results from the speedo model. So how do you test whether it does better on a longer time scale? So here we're doing a doubling of CO2 experiment. The top left panel here shows you the change in wind at 850 hectopascal in the perfect model. So you can see, for example, the strengthening of the westerlies in the southern hemisphere. The errors of the 3 different of the supermodel and the 2 imperfect models are shown here. These are connected by their atmospheric states in the supermodel, and tuned to and using machine learning to reproduce the perfect model. And this is now the error in the response. So you can see that the supermodel has a much lower error, and you can see the RMS value here of a 0.37 compared to 0.49 or 0.68 globally. So the supermodel is a dynamical system that actually reproduces the change better than the individual models. So just to wrap up, I believe we have supermodeling as a new avenue to improve climate prediction. It's an interactive combination of models. It's sort of, you could think of as a smarter way to do ensemble modeling. Compensation of errors at an early stage can reduce structural errors which would otherwise be enhanced by nonlinearity, and you get these common bias patterns that cannot be corrected by averaging them afterwards. The improvements can be greater than the standard ensemble approaches. And I've shown you that we can get improvements in short-term predictions, as in this case was weather forecast, and in long-term predictions or projections. The next stage for us is actually to look at the prediction problem, climate prediction problem. So thank you very much for your attention.
Thank you, Noel. More talks on showing the possibility of fixing errors. That's exciting. Our next speaker is here in the room. Is Greg Hakim from the University of Washington.
Thank you. This has been a wonderful meeting for me. I've learned a ton, and I expect to continue to do so for the next day and a half or so. The two topics I'd like to focus your attention on and hope that you remember from this talk are that forecasts need initialization. We've heard a lot about that so far this morning, but we haven't heard about coupled data assimilation, which is ideally how we get information from one medium to the other. And that requires using observational information effectively. And the second one is that forecasts need verification over a large sample of variability. And that's going to naturally take us out of the instrumental era and bring in the importance of proxies. Okay, so there are three main challenges as I see it. The first one is computational. Running Earth system models with relatively large ensembles for millennia is still a tall order. There are observational challenges. When you think about decadal forecasts, Argo is wonderful, but n equals 2 is a tough thing to do confidence tests on. The satellite period maybe doubles that. And even the instrumental era, I would argue, is too short. We got like n equals 10 or something like that. And it's all happening during a strongly forced period of the climate system. So therefore, I think bringing in paleoclimate proxies and extending the sample size to order 100 or more is really important. And the third challenge is strongly coupled data assimilation, where observations for the atmosphere, for example, can be used to inform the place where the memory resides in the ocean or potentially in the cryosphere. And the computational burden is even worse here because we have to add this on to the first bullet. And that's led to many approximations, some of which we've heard about in this meeting. So recent progress on the computational end. I'm going to talk about linear models, emulators, linear inverse models. They have a relatively long history in this community, but not for data assimilation, which is what I'm going to talk about today. There's been progress observationally, so we have an extension of reanalysis back prior to the satellite era, covering the entire 20th century, back to the mid-19th century, but also now going back a couple millennia by bringing proxies in. And I'll talk about one of those, the last millennium reanalysis. And finally, strongly coupled data assimilation, where especially pre-instrumental, and most of our proxies are terrestrial, is essential to get the memory into the ocean where it comes from. So I'll show two examples. One, the last millennium reanalysis, and the second motivated by the results and the techniques we came up with to bring it back to shorter timescales on S2S, where there's similar problems. So the LMR, as we call it, is a gridded global multivariate reanalysis. It aims to be like the standard reanalyses that we use for climate analysis. It's on the 20th century reanalysis grid, 2 by 2 degree, and there's a relatively large number of variables in both the atmosphere and the ocean. Both the data and the code are open and freely available. There are 3 versions, the most recent of which uses online data assimilation with a LIM, and that's what I'll focus on here. This is work that Andre Perkins did for his PhD. The first thing he did was to build a coupled LIM on annual timescales. So we just need a little bit of skill in an annual timescale to carry the memory of previous observations into the future. And what we're looking at here is a comparison between one model that he trained a LIM on, the CCSM4 last millennium simulation. Its power spectral density and these quantities shown in the 4 panels, SST upper left, PDO index upper right. the North Pacific Index in the lower right, and Nino 3.4 in the lower left. The raw model data is in the blue curve. The limb is in the orange curve with the 95% confidence bounds in the shading. So you can see that the model captures the variability in the model. And not only that, it has produces skillful forecasts on decadal timescales, as I'll show you. And that's critical because this forecast is basically free. You can run it on a laptop many, many times. So here's an example of the LMR online using only proxies. And the proxies are primarily coming from trees. We have some corals for the last 3 or 4 centuries and ice cores, mainly over high latitudes. And what you're seeing in the upper panel is the Northern Hemisphere average of 2-meter air temperature. The LMR result is in the black line, and it contrasts with a variety of other reconstructions in the colored lines. And what you'll notice is, especially in the medieval period, the LMR online is quite a bit colder than previous reconstructions. And that actually agrees fairly well with the only instrumental estimate we have going back centuries, which is borehole thermometry, shown by the dashed black line. And that's because of the ocean, especially the upper ocean heat content is carrying the memory of the sparse proxy network we have before this time in the first millennium of the Common Era. Down below, we're looking at validation on instrumental products for Aura 20C SST on the left and upper ocean heat content in the lower right. And it shows that the LMR, just based on proxies and a limb, verifies quite well spatially with respect to the Aura. More instrumental validation relative to sea surface temperature and these other variables. Especially intriguing is the upper ocean heat content going back to the late 19th century, early 20th century, compares really well with the Zana et al. Reconstruction of upper ocean heat content. But the high frequency variability too, like ENSO and the PDO, seems to verify really well. And again, this is just coarse proxies, noisy proxies, and a limb. Now, grad student Lindsay Taylor has taken this a step further to what we're talking about here, extending the sample size and making decadal predictions from these analyses over millennial timescales. So the sample size here is large. And she's got 2 limbs. One is in the black line, showing the forecast of global mean air temperature out to 10-year leads. That's the limb that comes straight from the CCSM4. And the red line shows you a limb that she has derived from the posterior of the LMR, that is after we've assimilated proxies, train a limb on the reanalysis. And it turns out that that produces both in sample and out of sample in the 20th century, more skillful forecasts than a limb that comes straight out of the CCSM4. So, based upon the success that we've had and overcome these challenges during the Paleo period, we've brought this back to much shorter timescales, to S2S analysis and prediction. And here we're looking at a limb trained on pentad data and doing strongly coupled data assimilation and looking at the benefit of strongly coupled data assimilation relative to control systems. So the controls here are an atmosphere-only limb that cycles on only atmospheric observations. And what we're looking at here in the color fill is the change that coupled data assimilation provides in the 10-day forecast relative to that control. And we do the same thing in the ocean. We have an SST-only limb that assimilates only SST observations. And then we compare how well the coupled data assimilation results and forecasts that derive from that differ. So what you can see is that there's lots of blue. Blue is good. And especially for the SST, there's a really large benefit in the global mean. It's 20 to 40% from assimilating atmospheric observations. The effect is larger during the in-sample period when we train the limb than it is in the validation period. And it's not quite as good for 2-meter air temperature. It's tough to extract information that improves 2-meter air temperature. It works quite well during the training period and not quite as well. There's still some skill, especially in the ENSO region. And this is mainly due to small sample size again. The statistics are non-stationary. Okay, so to summarize, the thing I want you to take away is that decadal forecasts need initialization with observations, and this is, I would argue, best done through strongly coupled data assimilation, which has been a frontier problem for 15 or 20 years and remains a frontier problem. And our decadal forecasts need much larger samples than we have during the instrumental era. And LIMS provide a way through this, and they don't have this initialization shock problem. And we can also understand the results. We can look at empirical normal modes in these LIMS, for example. So they produce skillful forecasts. Every model can have one, can have more than one, actually. They're fast to the point of being free. And they provide a null hypothesis for machine learning. So if you're developing a sophisticated nonlinear emulator, that's wonderful. It's got to beat the null, the linear model, which is understandable. A couple of notes at the bottom. If you happen to run into your favorite program manager, please tell them how important this problem is. It's very, very hard. It's multidisciplinary. Thanks for the plug if you get the chance. And there's a meeting on this subject in a couple months here in Boulder. Thank you.
Thanks for keeping us honest about verification of decadal forecasts. We have one more speaker, the fourth one, Leonard Borchert.
Thank you so much. So hi everyone, I'm Leo from IPSL in Paris, and I want to present some work that I've done with some wonderful collaborators here in Paris, namely Matthew Menery and Juliette Mignot, and some other people as well. And that work is about kind of tricks or approaches to use the currently available means and currently available simulations to harvest skillful predictions that we might not be able to see at face value. Now, as we've seen and heard during this workshop and also during other meetings, predictions are expensive, and while there have been significant improvements and advances, they still somewhat hold low skill, and that is specifically true and especially true over land and for beyond the forcing. To exemplify this, we already seen figures from this paper, I think yesterday. Martha Buckley showed a few. I'm showing here prediction skills, so this is anomaly correlation coefficient for unforced summer temperature for CMIP5 multimodal ensemble. Unforced here means that the multimodal historical ensemble mean was removed from, was used as a sort of a proxy for the forced response. It was removed from both the predictions and the observations before calculating skill. And what Doug Smith et al. Showed here is, well, that there's essentially not a lot of skill left over land when you do this on the decadal timescale. So this was, I think, 2 to 9 years. Now, we've done this too, and specifically, we've essentially repeated the same analysis, but with CMIP6 models. And if you look at that with a focus over Europe, it gets even worse. That is mainly related to the fact that CMIP6 models appear to pick up forcing response quite a lot better than the CMIP5 models did. So there's just much more skill in the historical simulations without initialization than there used to be in CMIP5. But this is obviously a problem, right? So if we want to predict unforced variability, then we need to do something about this. Now, one way to go about this is improving the models, improving resolution, improving data assimilation or initialization procedures, or increasing ensembles, all of which is absolutely necessary and very valuable, but it's also very expensive. So we were wondering, what can we do until we get there, until our models get so much better than we can actually predict these kinds of things. So the question that I'm answering or trying to answer today, and I'm going to present 2 sort of cheap, quick and dirty fixes to these problems with currently available means, and seeing if we can harvest physical process understanding to get a little more skill out of the models that we already have. Now I'm going to show this for decadal predictions, unfortunately, but I would like you to take this sort of as a motivation or an idea and inspiration for maybe future activities on the multi-year timescale as well. The first approach that I'm going to present is something that we call a dynamical statistical prediction. For this, we essentially fill in the deficiencies in dynamical prediction models using statistical models based on process understanding. The underlying idea is this, and this was, for example, used by Isla Simpson et al. 3 years ago, for fall precipitation over Europe. Essentially, the first step is building process understanding by deriving a link between a predictable and an unpredictable quantity or variable, for example, between the ocean and some atmospheric variable. Then, secondly, predict the predictable quantity on the decadal timescale, and then derive the prediction of the unpredictable quantity, so in this case that would be the atmosphere, from the decadal prediction of the predictable quantity, so say sea surface temperature. To illustrate this, in this work we tried to predict European summer temperature from spring sea surface temperature predictions. So we used dynamical predictions of spring sea surface temperature up to a decade out, and then derive summer European surface temperature predictions from that. And we're focusing here specifically on the unforced part according to the Smith et al. Method from the slide before. We do this by training our model, the statistical model, on HAT-CRU and HAT-ISST observations. And what we find is that European summer temperature correlates highly to Eastern North Atlantic and Mediterranean spring sea surface temperature. And that is relatively independent on the period. We chose to train our model on the 1900 to 1969 period because that is independent of the evaluation period that we're going to look at later for the predictions, which starts in 1970. Vice versa, we found that this index of spring sea surface temperature that is highlighted here in this blue box projects onto or correlates to summer surface air temperature during the same period over Europe, which gave us some hope that this model could actually work. And then to satisfy the second criterion for the underlying idea, which is predict the predictable quantity, we needed to check whether there's predictability in spring sea surface temperature in this area. And we found that sea surface temperature in this area in the CMIP6 multi-model decadal prediction ensemble is highly predictable. So this is all very promising to apply this now to the problem of predicting unforced variations of European summer temperature. And that's what we do here, which is testing the dynamical statistical model. So this figure you've already seen on my introduction slide. So this is the skill for unforced variations of an 8-model CMIP6 multi-model decadal prediction ensemble at lead years 2 to 9. European summer temperature, or summer temperature, as I said, over much of Europe, there's not a lot of skill. So here's the fourth step of our dynamical statistical prediction after building the model is estimate the skill of the model, which is based on the spring SST index prediction. And we find that this dynamical statistical model is skillful over much of Europe, especially over the south, and there's even statistically significant skill increase in some of the regions, specifically this southeastern part of the area that we are looking at here. So if you're interested in any details about this, yeah, feel free to ask me personally, or also have a look at the paper. This is published last year in Environmental Research Letters. So this is the first thing. The second approach that I want to briefly touch on is analog techniques, which I think were already also introduced by Hui Ding yesterday, but now we're looking at decadal predictions of the North Atlantic subpolar gyre. The underlying idea is to mimic initialization by just sampling existing model simulations, in this case, the CMIP archive. So the way this works is, let's say we're at this point in time and we want to predict into the future. So what we did here was we looked at North Atlantic sea surface temperature in the 35 years prior to that point in time and compared this using root mean square errors to all possible 35-year chunks in the CMIP5 and CMIP6 archive, pre-industrial control, historical projection, and DAMIP simulations, which gives a sample of more than 100,000 time slices of 35 years that we can compare this to. And then we selected the 100 best fitting time slices and extracted the next 10 years, which are shown in blue here. These are normalized to get rid of particularly strong variability or to reduce the impact of particularly strong variability models. And then we form an ensemble mean and use that as a forecast from that year. And we do that for every start year to come up with predictions across the time series. And you can see this here, the resulting predictions here. So the cyan line is the observation low pass filtered. The pink line here is the initialized decadal prediction system. The green line is the historical simulation multimodal ensemble mean. And the red line is the analog prediction. And you can see that this is similarly skillful as the pink line, so as the initialized decadal predictions, and even catches this decrease here at towards the end of the time series. So this is a highly skillful model. And this is just based on a really simple technique. So I think there's still quite a lot of room for improvement. For example, improve the selection method using machine learning techniques. We're working on that right now. Or extend this to European climate and see if we can predict something there using a similar approach. All right, so what I'd like you to take home from this presentation is, well, I was wondering whether there was any way, easy, quick and dirty way to extract skill beyond the face value of decadal predictions. And I presented two examples that we had, that we examined, which was dynamical statistical and analog techniques. For the dynamical statistical model, I showed that there is potential for skillful decadal prediction of unforced Southern European summer temperature, and details are in the ERL paper that we had last year. For analog predictions of subpolar gyre sea surface temperature predictions in the North Atlantic on the decadal timescale, we showed that there is pretty much similar skill in analog models as in initialized decadal hindcasts, which is also promising for future endeavors, I think. And with that, I thank you for your attention, and yeah, let's discuss.
Thank you, Leo. Thanks to all the speakers for these great talks. We have a bunch of questions online, so why don't we start with the first one from Annika or Tom. Annika, if you're still there, would you mind asking the question?
I'm here. Hi.
Hi.
Can you hear me?
Yes.
Yes. So I was wondering. I was at Hakim's poster yesterday, and he introduced me to their prediction system and told me that they initialized the ocean by spinning up the ocean-only model with atmospheric forcing. And now Tom presented his system, and if I'm not mistaken, you use the coupled mode, coupled atmosphere, and then you have a 3D forcing of the atmosphere, right? So how is that different, and why do you do that? Isn't that more expensive?
Thanks. I guess it might be a little more expensive, but our philosophy was to try and get a more consistent system. And this was just sort of a, see if this would work. I think it works pretty well. So that when we are initializing, or when we're going through the reanalysis to build up initial conditions, we are trying to tightly constrain the atmosphere and the ocean so that the fluxes computed between the air-sea interface will mimic observed fluxes, because that's the only thing the ocean is going to feel, is what are those fluxes. So we want to try and create a system in which a coupled system in which the ocean is being driven by fluxes that are pretty close to the observed fluxes. And then all we have to do is stop the model and take off the constraints and run it. So it's pretty simple in that respect, but we feel as though it's consistent. And the idea was to just try and make a system which is less subject to shocks, and I think it is. I think the drift is very, very small in the system. I think partly because we do it in a coupled framework. Thank
So
you.
you don't have any strange drift in the ocean if you run that for some decades?
No. It's quite good, quite nice. And in our older system, we had CM 2.1. We had done direct assimilation of conditions, and to be honest, I found it a bit disappointing because for example, the AMOC, the overturning circulation in the Atlantic, is very dependent upon density, and how many salinity measurements in the subsurface do we really have in the Atlantic, and are they co-located in time and space with temperature, which is what you need to get density? I found that actually quite daunting, especially when you go back prior to the Argo period. So this was a little bit of a way to finesse that has inconsistencies, at least in my mind, in trying to bring those sparse, sporadic ocean observations into a system. We let the atmosphere create the fluxes and drive something. And when you look at the subsurface ocean in this system without any injection of subsurface ocean information, it's pretty good. So we're think this, at least, it's there are multiple ways to do this, and I don't say this is better or worse, but it's different, and we like it.
Thank you.
Thank you.
We have a question from Jerry.
Yeah, so I think just to follow up on that question, Tom. So the FOSSI system basically does the same thing. It uses atmospheric forcing on the ocean, but you run through 5 cycles of it to try to imprint that and get that further down into the upper ocean. Do you just do one cycle of your forcing?
We just do one cycle.
Okay, so what do you use for your ocean initial state when you start that up?
We take it from one of our historical simulations. We have lots of those lying around. So I think that it's been a while ago. So we might, I forget, but we might say repeat the 1950s or something to get a little bit of away from initial drift. But we don't cycle through multiple cycles over the whole period. If there's I think we do like repeat the 1950s or something. But after that, we charge straight through.
Okay, so the implication for me, looking at the fact that you're getting no drift in your predictions, is that your ocean is pretty much in its systematic error state, in the ocean models, in its systematic error state, and you're kind of treating the ocean like a big slab, right? So you're only reacting to the SSTs. The subsurface ocean is not drifting anywhere because it's in its preferred state already. So is that kind of the way you're interpreting this? And it kind of goes back to these experiments where a lot of these decadal timescale phenomena can be simulated in a slab ocean coupled to an atmosphere. Is that kind of where this is headed? Is that?
Yeah. Actually, no, I wouldn't go that way, because all the fluxes that the coupled system feels, that the ocean feels, are the full range of fluxes. So wind stresses, operating buoyancy fluxes. So when you look at, for example, the AMOC in this reanalysis, it actually agrees reasonably well with the say rapid array. So the ocean is fully dynamic in this. It is absolutely not a slab ocean. So it folds the full range of things. We see, the North Pacific gyre circulation. We saw these excellent reanalysis of the Kuroshio extension yesterday from that Jing-Jia Luo showed. So it's absolutely not a slab ocean. It's getting the full range of fluxes, and the dynamics of the ocean are in full play.
It'd be great if you're here, because I'd like to talk to you about this more, but
oh yeah, sorry.
Yeah,
no, I would love to. We can chat sometime, but I think it's actually this whole approach we're doing was quite inspired by the NCAR approach, and we think that was very good, and we thought we'd do something a little bit different. But I think every approach has strengths and weaknesses, and so it's quite nice to compare things.
We have a question from Nikki.
This is also for Tom, a little bit of a follow-up from the chain of questions you've been getting. I'm wondering if you have plans to incorporate some of the ESM for carbon cycle or ocean biochemical aspects of the GFDL activities into the SPEAR prediction system. And in particular, I'm wondering about the new biochemical Argo float data, whether there's plans to incorporate that in your short-term seasonal forecast system.
Right. We have lots of discussions with John Dunn, Charlie Stock, and others about that. And we definitely have aspirations to do that. Exactly, when we're going to do that is unclear, but absolutely it's in our plans, and it's something we really want to do.
Great. Thank you.
Hey, Tom. We have a question from Judith for Noel. I see Judith on the screen.
Hi, hello. Hi, Noel. Thanks so much. I really enjoyed your talk. and I'm not sure if I have a comment or a question or maybe more a comment. I think it would be, so I guess the first question is, do you understand why the synchronized model do better and why the model error is smaller? And the second is, I think it would be great if you look at, I guess, the interaction coefficients or the tendencies that then bring one model closer to the other one. And have you analyzed those to understand where is the model error coming from? And can this technique maybe then be used to improve an individual component model? So it's really physics questions. Why is it so good?
Yeah, thank you for the question. We've been thinking about these type of things quite a lot, and I think I can't answer the question properly. So essentially, we're correcting errors. So it's a little bit related, I think, to what Tom Delworth has asked in the chat as well. So in our approach, we recognize that subgrid scale parameterizations are a root cause for errors, and that it's the interaction between the subgrid scale parameterizations and the large scale. So that you have errors in the subgrid scale parameterizations and how they interact with the large scale. At large scale, you will develop these large scale biases. So with the supermodeling approach, we aim to, in the different systems, how these interactions occur, we balance these at an early stage so that the errors don't develop. So we've looked at one situation in the tropical Pacific, so where we corrected the double RTCZ in an earlier paper, and we tried to understand why. So the second part of your question, and we found that it was, small differences in the wind patterns between the two different atmospheric convection schemes that we had implemented, and that these two error differences would lead to a common error, which is this double RTCZ, but they actually influenced the ocean in slightly different ways. So, and by balancing this, we could control the sort of I would say Bjerknes feedback effect versus an off-equatorial effect. And so we could correct the error this way. But we couldn't actually get to how to improve one model. We haven't got that far. We sort of understood this part of the problem, but it's very complex because of this scale interactions. So if you have any ideas about how to address this, I'd be really interested to. It's a shame we can't not in one place. We couldn't discuss better. Thanks.
Thanks.
Thanks for the great question. We have a question for Leo from Adam Skype. Adam, are you there?
Yeah, I'm going to read exactly what I've written, as it's a little bit long and I tried to word it carefully. Hi, Leo. Thanks for a nice presentation. So while I agree that there is merit in your dynamical statistical approach, I very much agree with that there is, if you take the large scale predictors, you can do a better job on the regional scale in many cases. I just wonder if you agree that there's also a risk of circularity when you select the predictors. So for example, if you selected a predictor variable or like your average SST that is highly predictable, and let's say that it correlates with, but does not cause the target predicand, then is there a risk we'll get good results by construction because we picked something that's correlated, but these might fail in future? I think this is sort of what's happened in some cases where people have used the sea ice as a predictor of the NAO, for example.
Yeah, thanks, Adam. I completely agree that is one of the dangers of this kind of approach, which is why I wouldn't necessarily. So I think there are two answers, or there's a two-part answer to this. The first part is that we have to be absolutely quite sure about the physics that are going on, because then we can know about the causal relationships. And if we have a causal relationship, then I think we circumvent the problem that you outline here.
Okay,
We're actually working on sort of trying to nail that down, and there's a little bit more about the physics underlying in the paper as well. The second bit is that I don't think this is going to be a permanent solution to any prediction problem. So I don't think on the long run anything can really replace model improvement or improving the prediction systems.
Okay, thanks. I agree with you. Thank you.
Thanks.
We have a question in the room.
Yeah, this is a question for Leo only. So every year you select the model ensemble, like 100 ensemble. Did you see like every year are the same group of model or their ensemble are being selected, or the different ensemble are selected, or what we can learn from that group of the selected ensemble?
This is a great question. We were quite disappointed that we didn't really see much of a systematic behavior in the selection of the models. So if you want to go to the paper, which was also published last year in ERL, the Menery et al., there is a plot in there that shows the composition of the ensemble that we selected with the analog approach. And there's not, we didn't find any obvious features. For example, that towards the end of the 20th century, we there were more models from the projection archive because those show a stronger trend or something like that. We didn't find anything like that, which we were quite disappointed by. But then I think it's also worth keeping in mind that the selection based on just simple RMSE is not particularly elaborate. So I think coming up with a smarter technique to extract something, I think we might be able to get also maybe more appropriate physical states, which might then also tell us more about the background climate of the predicted period.
Thank you. We have some more time for a question. I have a question for Greg, since no one asked him a question. Do you know why the Alamar trained limb is better than the CCSM4 trained limb in those predictions that you showed? What makes it better to train on the Alamar?
The short answer is we don't have a definitive answer to that question. I would say it's one reason why we have not yet submitted that work for publication. But ultimately it comes down to there's something in the proxies on low frequency timescales that's different than what the model dynamics are doing. So I think that's the simplest answer. We've learned something from the proxies.
Awesome. I look forward to reading the paper. Okay, more questions. We're gonna go to 10 to the hour.
Thank you. I have a question for Gregory. Your Ensemble start from 1979. Is there a reason why you start from that date?
Ensemble for the results that I showed?
Right.
No, well, the ensample for the LMR was 1000 to 1850 CE, and then the out of sample was 1850 to 2000.
Thank you.
You're welcome.
Hi,
Hayan
Hayan, you have a question.
Oh, yeah. I have a question for Neil. I wonder whether, Neil, you can explain a little bit more how you applied the machine learning correction to the supermodel. For example, did you correct the supermodel at every time step? And would you expect, or would you achieve similar effect if you apply this machine learning correction to a single model? For example, running a simple model and machine learning model, like a hybrid model.
So just to answer the first part of your question, in the case of the speedo models, we connected the atmospheres every time step. And so the correction, the machine learned correction was done every time step. So it was trained on a certain period and then it was fixed. For the ESMs, we connected the models once a month. So we estimated the correction monthly. So there's a sorry.
The improved skill, I just wonder whether if you apply a machine learning tool to a machine learning model to a single model, can you achieve similar improvement? Because you are comparing machine learning corrected supermodel with a single model. and it's not a fair comparison because you didn't run a machine learning correction to the simple model.
So we might try to train a simple model, the parameters in a model. I think we haven't done that, but we would expect, based on the CMIP experiments, that you wouldn't get a better model. You wouldn't get a model that approached the supermodel. But it's,
okay.
yeah.
Thank you.
Thanks.
Well, thanks everyone for the great questions. We're going to go into the breakout discussions, and another round of applause for the speakers.
Thanks, everyone. That was a really interesting session. I know there were still questions at the end. That's what the Slack is supposed to be for, everybody. So please feel free to put your questions in Slack for both this session and the previous sessions. Speakers, check in if you see any questions. Feel free to discuss. People can just drop in and discuss too. That's also okay. We're running a little behind, I think, because we want to make sure that we have enough time for the breakouts. We'll just add 15 minutes to the times on the schedule. So we're going to go to the breakouts now. Same breakouts as yesterday, same groups online. I think we have one breakout, at least for now. We'll see, I guess, how things go. In the room, there were the three. We're going to end at 11:40. So we'll have lunch from 11:40 to 12:40. And then we'll have an hour and 20 minutes for the poster session, which I think should be okay because I know we have a few less than we did yesterday. So let's do that and then come back here promptly at 2 for Jing-Jia, who's actually giving the last talk in this session, but is in Australia. And I thought it would be kind of cruel to make him talk quite this early. So everybody, we'll see you back then.
Welcome back, everyone. We're gonna get started now. Our next speaker, an invited speaker, is Jing-Jia Luo. We'll be talking about deep learning of multi-year ENSO events. Feel free to post any questions on the chat. We'll answer them together with the next session. So we'll jump right into the next session after Jing-Jia's talk. Jing-Jia, all yours.
Oh, thank you. Can you hear me? Hello, can you hear me? Yeah?
Yes, we can hear you.
Okay, thank you. Thanks, Matt, for the invitation. Actually, I'm Jing-Jia Luo from Institute for Climate and Application Research, ICAN in Nanjing. This PPT actually was prepared 2 years ago. I hope the content is still of interest to you. During recent years, you know, the artificial intelligence technique has attracted much more attention. Here I will show you one example using a deep learning method to forecast ENSO and Indian Ocean dipole. Can I go? Oh, okay. So in my talk, I will first briefly introduce current skill in predicting ENSO using dynamical models. And then I will introduce very basic principle of machine learning technique called convolutional neural network, CNN. And I'll compare the CNN model skill with the current dynamical model skills, and then briefly issue a kind of perspective. So we know that a tropical climate has very large impact on global climate, environment, and society. For example, the strong ENSO El Niño event always trigger big flooding in China in following summer. And ENSO also has very big impact on the crop yield in over global scale. So that's because of the large impact of tropical climate. So many understanding and predicting ENSO and IOD has become a key issue since past decades for many major operational center has put ENSO forecast as a key metric, key parameter for their seasonal forecast. So since the first successful forecast of ENSO using a dynamic model is made by Kane et al. In 1986 using a very simple couple model. And since then, in 1990s, a few American centers developed a kind of a flux corrected global model for ENSO forecast. And in 2000, some European centers, they set up the MID project and develop a fully coupled global model for ENSO forecast. This shows one example in 2008, and by Jing et al. They collect 10 couple model at that time, this model shows a forecast of ENSO up to 6 months lead at that time. So you see that most of the model actually can issue good skill compared with this persistence forecast. And since then, many centers, including North American multimodal system, they try to extend the forecast lead time from 6 months to 12 months. So this is a forecast of a fall and winter Needle 3.4 index. And you can see actually among them, the 3 model actually can show very good skill up to 12 months. And the blue line shows our model, our dynamic that developed in Japan and also in Nanjing. You can see that actually the model shows kind of good skill up to 12 months. And indeed in 2008, we actually extended the ENSO forecast from 12 months to 24 months ahead. You can see up to 12 months, our skill is up about 0.7, and at 24 months lead, the skill is 0.5. So approximately is 75% of hit rate. So that's quite a reasonable skill. And since I returned back to China in 2008, we also issue real-time forecast of ENSO and IOD up to 2 years ahead. This forecast updated monthly, regularly. So every month we update on the forecast on the website. So this shows a sample example, like for any forecast from January 1st, 2019 and October 1st, 2019. You can see that this El Nino in 2019 was actually forecast pretty well. And also we know in 2019, there was a strong positive IOD event happen. So in the Eastern Indian Ocean, the SAT norm is much colder than the normal during the summer and fall in 2019. So the IO model actually shows quite a good skill in forecast this strong, extremely IOD event. So in addition to these indices, we also provide a global map of temperature, sea surface temperature, air surface temperature map, and also rainfall circulation map on our website. So if you have interest, you please look at our website. They are updated monthly. So the most popular ENSO real forecast was provided by RI, Columbia website. They gave them about 20 dynamic model and 10 statistical model forecast. So statistical model forecast, statistical forecast model actually was developed much longer, much earlier than dynamic model. Although many forecast centers now, they basically use dynamic model for real-time forecast, but the statistical model still can provide a helpful and useful, sometimes comparable skill in ENSO forecast. So here we try to develop a new kind of a new type of statistical forecast model using a deep learning method. So this idea actually was stimulated in 2016 by AlphaGo. AlphaGo is a deep learning algorithm for a Go game. So 2016, it beat the Go champion in South Korea and China. So that's actually caused much attention in the society. So the artificial intelligence actually was first proposed in 1950s. Since then, it has been developed quickly, but not always smoothly. So the latest development of artificial intelligence techniques is mostly focused on deep learning. So one of the a well-known example of method of deep learning is convolutional neural network. So it mimics human visualization scheme and decision-making process. So all basically all deep learning method contain input layer, hidden layer, and output layer. So different algorithm has different hidden layers. So in the CNN structure, it contains convolutional layers and pooling layers, and then second convolution layer, second pooling layers, and third convolution layers. So it's not just one layer; it's a Lanet 5 structure. So it's a deep learning method. So after we get the key pattern of the input data, and then we use the full connection layer to do our job. So for example, we use a CNN model to extract the basic structure of predicators, and then we can use that predicator feature to forecast the ENSO index. So the key components of CNN model is convolutional layers. This shows how the convolution works. So the green box is 5 multiply 5 matrix, and the moving orange 3 by 3 box shows the filter. So the red digit shows the filter. It's kind of weight coefficient. So a simple filter, convolutional filter, is kind of a two-dimensional Laplace operator. So the second order differential operator can capture the edge of an image. So that's why. So all the convolutional filter actually try to extract the regional feature of a regional pattern. So, for example, the filter can scan the whole input data and then do the convolution, and then get the convolution convolve the features. And after that, we use a threshold function, which is a nonlinear function, and we actually project all the input convolutional features from like minus infinite to plus infinite to the value from -1 to +1. So because the threshold is nonlinear, so in principle, this process can actually help capture the nonlinear relationship. That's kind of benefit compared to the traditional linear method. So after we get this convolution convolved features, and because the data set is quite large, so we need to do some kind of pooling process to reduce the data, speed up the calculation, and also help us to extract the most important features. For example, we got with the convolutional values in like from 4 by 4 a matrix, and then we split this box into 4 small regions, and then we select the maximum value. And from this box is 6, from box is 8. So in this, so we select the maximum value from each small regions. So in this way, we can keep the most essential, most important features and reduce the data size. So this is actually the key 2 key layers of CNN structure. And because the CNN is very good at to recognize the image, so it has been widely used for face recognition. So and also automatic car driving. So this help you recognize the in the front of car it's a human or it's a tree, something like that. And also it's very good to identify the different objectives in the one pictures. So that's this is kind of a good point of the CNN, and it's very good to find a pattern of predictor for a predictant. So in our ENSO forecast model, our predictor is from global sea surface temperature anomaly and global upper ocean 300-meter ocean heat content. So during 3 months prior to the start date. So we input these predictors and using the Leonard with several convolution layers and max pooling layers, and then we use fully connected layers to connect this the global feature of the predictor to the ENSO index. So this is the Leonard. It's a popular CNN structure used in AI areas. And for each lead time, we perform a forecast at 1 and 12 4-month lead. So for each lead time, we build the CNN model, and so that's we have 24 CNN model for different lead time. And for each lead time, we also develop 10 CNN models. So we use the 10-member ensemble mean to get our final forecast result. So and one important issue is that all the deep learning algorithms require big data set, but we know the ENSO event happen every year. So even we have 100-year record, we only have like 40, 50 events. So that's a very small sample. So solve this issue, we use a kind of transfer learning method. So we use a simplified multimodal historical norm over the past 100 years. So we have like about 30 models. So some models have many members. So we have like many thousands or 10,000 years. So that's probably kind of enough data set. So we first use a simplified historical norm because this model actually have a reasonably good performance in simulating ENSO, the features, the patterns. So that's similar to the observation. And we use this kind of this model result to first training our CNN model. So we get all the optimal optimized filter, like a wet coefficient. And then we use okay.
We're running out of time.
Okay, sorry. And then we use the observation to retrain the model. And finally, we use this CNN model for the past hindcast of ENSO. So this is a result.
That's 2 minutes.
2 minutes. Okay, so thanks. Sorry. The red line shows the CNN models. So now you see compared to the dynamic model, up to 12 months lead is the skill almost similar with our model. But at the longer lead time, particularly like for the DGF forecast in 18 months lead, so it's the skill is much higher. And so another benefit is we know ENSO has spring barrier. So all dynamic model has problem in forecast spring time ENSO signal, and the CNN has very good skill. And also compare with the ordinary machine learning technique like feed-forward neural network, the deep learning has much better skill than the ordinary machine learning skill, and also has better skills than forecasting in the spring barrier. And also because CNN has very good skill in capture the spatial pattern, we can use this method to forecast the different type of ENSO. So that actually CNN shows very good skill compared with the dynamic model. And last year, we actually organized a global competition for using AI for ENSO forecast. And we attracted more than about 3,000 teams from worldwide. And also we had a climate exchange issue for the ENSO forecast, climate forecast using AI. And recently, a student also used CNN and a similar method and develop a IOD forecast. And again, the red line is the CNN forecast compared with this dynamic model. Again, the CNN shows a pretty good skill compared with those dynamic model, including the correlation skill and the root mean square error. So this is my final slide. So actually, the machine learning technique has been applied in many areas of climate study, weather study. In addition to climate prediction, also it's it has been popularly used to identify like tropical cyclones as extreme weather condition and weather forecast, and also ocean forecast like sea wave forecast. And also it has been used to forecast renewable energy like windy energy, and also for data simulation and numerical model development. So many kind of subgrid physical process parameterization can be replaced by the AI techniques. So I stopped here. Sorry, I used too much time.
Thank you so much. If you have any questions for Jing-Jia, hang in there, and Jing-Jia also hang in there. We'll go back to all the questions after the next session.